Hello everyone, I'm really excited to have got a chance to deliver this lecture today to you all. I would like to briefly introduce myself. I'm Smita, currently working as a postdoctoral research associate at Durham University in the UK. I'm working on a project on fungi biopolymer synergistic application on soil stabilization. So now my current lecture is on the topic of biopolymers in soil stabilization, its mechanisms, performance and design. Moving on to the learning objectives. The first one is to understand the role of biopolymers in soil stabilization, to explain the mechanisms by which biopolymers enhance the soil properties, to evaluate the performance matrices of biopolymer treated soils compared to cement-based methods, to apply a design considerations for field application and sustainable geotechnical practices. So before we get into biopolymers, let's first talk about why we even need something new for soil stabilization. Right now, we mostly use cement and chemical additives to make weak soil stronger, right? So they work really well actually, but they also comes with a pretty big environmental cost. Cement, for example, is one of the biggest source of industrial carbon emissions. It's responsible for almost 8% of the world's CO2. Plus, when we add chemicals to soil, we know it can disrupt the natural ecosystems, making it tough for plants and microbes to survive after construction. To put it in perspective, if we could just replace 10% of the cement with greener materials, we could cut about 6 million tons of CO2 every year in geotechnical projects alone. That's huge, right? So now engineers are looking for smarter eco-friendly options, something that can still give us strength but without damaging the environment. And that's where biopolymers comes in. They are natural, renewable and biodegradable and can be a real step towards sustainable soil improvement. So let's see what they are and how they actually work. So what are biopolymers? It's actually from the word, we know it is bio plus polymers. So let's start with the basics. So what are polymers actually? You might be already knowing, but I'll just brief you about it. So they are basically large molecules made up of small repeating units called monomers. These monomers are linked together by strong covalent bonds, forming long chains, sometimes with thousands of repeating units. So here you can see a polyethylene image, structure of a polythene image. This is actually a really common example, which is the plastic we see in the things like bottles or bags, etc. It's a synthetic polymer and the chains here are mostly linear, which gives it flexibility but also strength. That's why it's so widely used. Now these polymer chain can have different structures. Some are linear, some may be branched, they might be cross-linked. So cross-linked means where the chains are tied together in multiple directions. So the structure of the polymer decides how it behaves. For instance, whether it's soft and stretchy like rubber or hard and rigid like plastic. But polymers don't always have to come from synthetic sources. In nature, we have what we call as biopolymers. These are polymers made from living organisms like plants, algae, fungi, or even microbes. They are biodegradable, renewable, and much more eco-friendly than petroleum-based plastics. So here you can see a common biopolymer starch. So this is actually repeating units of glucose molecules linked together. And the structure gives this structure of the starch gives it a binding and thickening properties, which is why it's used in food. But interestingly, it also works really well in soil stabilization, helping bind the soil particles together in a natural way. So in short, synthetic polymers gives us strength, but biopolymers gives us strength with sustainability. And that's what makes them so important in modern geotechnical applications. So the biopolymers might sound like a modern innovation, but people have actually been using natural organic materials for buildings and soil stabilization from past thousands of years. Ancient civilization used things like bitumen, straw, and even sticky rice as natural binders to strengthen their structures. One of the most famous examples comes from ancient China, where builders created a sticky rice mortar. They mixed sticky rice soup with lime, loess, river sand, and produced a mortar with high strength, good toughness, and good water resistance also, which is why many of these old walls and temples have survived for centuries. So in a way, using biopolymers today is just reviving an old sustainable idea, but now we understand the science behind it much better. So these are some of the common biopolymers being used in geotechnical engineering. You might be familiar with some of these like agar-agar, which comes from red algae. It's actually more commonly used as a culture medium in labs and also as a thickener in food. Then xanthan and guar gum, they are also common in food and pharmaceutical industries, where they act as stabilizers and thickeners in things like sauces, toothpaste, and even ice creams. Then starch from corn or potato is also a common one. There are other biopolymers like lignin, which is obtained from industrial byproducts or pulp industries. So why biopolymers? That's a question, right? So they are becoming popular because they are a greener and safer alternative to cement and lime. They are also natural and non-toxic, so they don't harm the environment or groundwater and can even support the plant growth. They also produce up to 90% less CO2, like considering their production stage, and also making them much more climate friendly. And since they are biodegradable, they break down naturally after doing their job. So they give us both a strength which we need and the sustainability which we want. Here I would be explaining the strength improvement mechanism. But before we go into the actual mechanisms, let's first see what happens when biopolymers interact with water, because this is really the key to how they work. So biopolymers are hydrophilic, meaning they love water. So when they mix with moisture, they form a hydrogel, which are actually soft jelly-like materials made of three-dimensional network that can hold a lot of water. So here you can see the SEM image. SEM is actually scanning electron microscopy or very high resolution images. And you can see these are actually glass beads which are mixed with beta glucan biopolymer. So beta glucan, it forms a hydrogel, and these are the hydrogel that bonds two glass beads together, and also it forms a like kind of film or web that coats and connects the particles. So that's the glue-like effect that helps even to bind the soil particles together. Now, there are actually three main mechanisms behind the strengthening. So first, the binding and hydrogel formation. Hydrogels that they wrap around the soil grains and forms thin films that hold them together. So these films can increase the cohesion and give the soil more rigid structure. As water content changes, the hydrogel can swell or shrink, helping the soil stay flexible instead of cracking. The second mechanism is particle interaction. At a smaller scale, the biopolymer molecules have active groups, things like hydroxyl and carboxyl groups. So they can bond with the mineral surfaces. They form hydrogen or covalent bonds which strengthen the contact between the soil particles. So this effect is especially stronger in clays and silt, where the surface area, because the clay particles are smaller, the surface area will be more for bonding. So the third one is pore structure modification. So the hydrogel can fill the pore spaces, reducing the permeability and erosion while improving the strength and structural stability. And these are the SEM images that shows this is actually agar biopolymer treated sandy soil. So here you can observe the hydrogel interlinking between sand grains and coating over the soil particles, and also aggregation and pore filling between the soil grains. Now that we have seen how biopolymers strengthen soil at the microscopic level, let's look at what actually means like in practice. So how these materials improve the soil performance in the laboratory or in the field. So the first image you can see loose sand on the left and the right hand side, the same sand after being treated with a biopolymer solution. So they can form, or the cylindrical specimen can stand by itself. So this transformation shows how effective the or how effective the materials can be. So this is actually with a very less dosage of biopolymer treatment, around 0.5 to 2% by weight of dry soil. So even with that much small amount, The transformation is very like interesting, right? The studies show that this treatment can increase the unconfined compressive strength by over 50% while also improving the cohesion and water retention. So the gel matrix formed by the biopolymer binds soil particles together, making the soil much more resistant to mechanical stresses and cracking when it dries out. So in other words, it doesn't just get stronger, it also becomes more flexible and resilient. So the second image is actually related to erosion control. So another major benefit of the biopolymer is its reduced permeability and erosion control. Like research led by Lee et al. 2023 showed that just 1% of xanthan gum can reduce the soil permeability by up to 4 orders of magnitude compared to untreated soil. That's a huge improvement. It's like literally like converting sandy soil to like fine silt or clay. So by filling the pore spaces and forming a gel network, biopolymer limit the water flow and seepage. It helps prevent erosion, especially on slopes, embankments, and river banks. So it is also useful under rainfall or flooding conditions, which is one of the biggest challenges in sustainable geotechnical design. So overall, the applications show how biopolymers can strengthen, seal, and protect soil, offering both mechanical improvement and environmental resistance. The another application is here you can see a picture from Tran et al. 2019 where two slopes are compared, one left and amended and the one stabilized with a biopolymer. After 1 year of study, it was shown that both slopes support vegetation, but the treated slope clearly shows a healthier and denser plant growth. So the biopolymers are compatible with vegetation and natural system. The study shows that their ability to retain soil moisture gives plants a better chance to survive, especially in dry areas. Additionally, biopolymers improve the soil structure, root anchorage, creating a more stable soil matrix for plants to grow. As already discussed, they also reduce the soil permeability and prevent erosion, which protects the surface layer and allows vegetation to establish even on the slopes. So on the slide, we are looking at biopolymer application for construction and like road pavements. The first image shows lignin stabilized silty soil being used as a highways upgrade material, essentially improving the soil strength and durability for road construction. The second image comes from Muguda, like study by Muguda 2019, where in his thesis it was shown that we have earthen blocks made with and without with stabilization and without stabilization. It was stabilized. The soil blocks were made with 2% of guar gum treatment. A simple dip test was performed, soaking the blocks in water for about 10 minutes, and the results are striking actually. The untreated block lost about 15% of its mass, while the biopolymer stabilized blocks lost less than 5%. So this shows how even a small amount of biopolymer can significantly improve the water resistance and durability, making soils much more suitable for construction applications. It's a simple but effective way to enhance traditional earth materials sustainably. So this is just the schematic representation of the applications given in a summary. So the already explained applications like slope reinforcement, then vegetation improvement, erosion protections are given here. Then biopolymer used for road construction is given here. Then there is a application like where in dry areas and windy regions there might be dust pollution. So in those regions, if we spray a layer of biopolymer solution over this, it might mitigate the dust pollution to an extent. So then other applications like deep soil mixing can also be explored. So just like any other cement or lime stabilization, the biopolymers can also be mixed in a deeper level and can be used for ground improvement for a larger scale or for liquefaction mitigation and such applications. Here we are comparing the performance of a biopolymer stabilized soil with traditional cement-based stabilization across several key matrices. In terms of strength and stiffness, the cement generally provide higher values which is why it's widely used in structural applications. However, biopolymers still provide significant improvement compared to untreated soils, enough for many geotechnical and low to medium load applications. So where biopolymer really stands out is its durability, permeability, and environmental impact. Biopolymers reduce erosion, improve water retention while also being biodegradable. So this makes them a more sustainable choice, and their carbon footprint is far lower than cement. So the takeaway is that while cement is stronger in absolute terms, biopolymers offer a balanced combination of adequate engineering performance and strong environmental benefits, perfect for a sustainable nature-based engineering solutions. On this slide, we are looking at some of the challenges and design considerations when using biopolymer for soil stabilization. The schematic diagram shows what happens when soils are exposed to water. You can see the unamended soil, biopolymer amended soil, and biopolymer soil when exposed to water. So because the biopolymers are hydrophilic, the gel swells and it can soften the hydrogel, which can lead to a temporary loss in strength under wet conditions. So this is actually a drawback. But when designing the biopolymer treatments, you need to carefully select the type of biopolymer based on soil type, climate, and intended application. And also scaling up from lab to field can also be tricky due to its cost, supply chains, and mixing technology. So the typical mix proportions range from 1 to 3% by dry weight of soil. And the proper curing under controlled moisture condition is also essential to achieve an optimum bonding and performance. So while biopolymer offer many benefits, successful application still it requires careful design, material selections, and field implementation. So it requires more research to be applied in field. So for further reading and reference, these are the references. For further reading, you can refer to the first two papers, one by Chang et al., which is a review paper, and the second is Liu et al. In 2023, where the performance of a biopolymer binder for clay soil stabilization was explored. So it has some mechanical properties and also microstructural characteristics are given. So that can be good for a future read or for further understanding the mechanisms. So thank you everyone for listening to my lecture. And in case of any clarifications or discussions, you can feel free to contact me in my email ID. So thank you once again.